So last time we started discussing the three topics: area, sums, and integrals. Now we will continue with that. We begin with the concept of a Riemann sum. So what is a Riemann sum? First, we have a function which is defined on some interval from a to b. So a is here, b is here. This is an example of a function which is defined on the closed interval from a to b. And such an interval can be partitioned into smaller bits. So a partition P of this interval from a to b is an increasing sequence. So a is x0, then we have an x1 which is bigger than x0, or x0, and so on up to xn, which is equal to b. So basically we have a finite number of points where the smallest of these numbers is a and the largest of the numbers is b, and all the others lie strictly in between. Having a partition, we can also have a selection. So a selection S for the partition P is a collection of points. So the points in the selection are called xi star, and they are in the subinterval from xi minus 1 to xi, where I runs from 1 to n. So clearly having these n plus 1 points, right? x0, x1, so on up to xn, we have n plus 1 points, and that gives us n subintervals. So in this case, we have one subinterval here, another subinterval here, another subinterval here, another subinterval here, and a final subinterval here. So in this case, n is 5, right? And we can have 6 points because we start at 0. Right? And the selections are then some number in each of these subintervals. It can be any of these, right? Even the endpoint. And having a partition and a selection, we can now find the Riemann sum for f determined by the partition P and the selection S, and it's given by this sum. Discussed this notation last time. I will now explain what it means in this concrete case. So this is just the functional value at the selected point from the selection, right? And the delta xi is the length of each subinterval, like this. So if you have an interval from xi minus 1 to xi, of course, the length of this interval will be the difference of the two numbers. So the bigger number minus the smaller number. So this is just the length. So in other words, each of these terms here, you can see them as illustrated here. You have the length here. Oh, that's maybe better here. The length of the interval here corresponds to delta x1. And then what is so that's the delta x1. And what is f of xi1 or x1 star? Well, it's the functional value at this point, right? So take the selected point, you see what is the functional value here. And then you multiply the two numbers. So what do you get if you multiply two numbers? Basically, you get the area of this rectangle given by these two. And that we can do for each of these subintervals here. And then we get some area, right? Except there's one thing we should be careful about. This number here, which is the functional value at this last point here. What is this? This is a negative number, right? So in fact, this is not the area of this rectangle, but it's minus the area of this rectangle we get. We could have had more points. I can just pull out some new ones like this. then we get, so down here you can see what my present partition is. My partition is -11, -7, -3, -0.39, 2, 6, 9, 15, right? That's just the values you can see here, here, and so on. And my selection then consists of some numbers. You can see there are one less. It looks longer, but this list, but that's just because we have more digits here. So here we have 1, 2, 3, 4, 5, 6, 7, 8 numbers, right? Because n is 7. Here we have 1, 2, 3, 4, 5, 6, 7. There's a mistake somewhere. 1, 2, 3, 4, 5, 6, 7. No, of course, 7. The other was, there were 8 up here, right? And this number is between these two numbers. This number is between these two numbers, and so on. And had all of these numbers been, or had all the functional values been positive, maybe I can just cheat a bit and make this. This would be an approximation of the area between the graph and the x-axis, right? So this Riemann sum is an approximation of what we have so far called the integral of this, right? So there are some last things I want to mention. So for any partition, so P is the partition, right? If we put vertical lines on both sides, we talk about the size of this partition. And what we mean by this is the largest of these subintervals. So a partition is big if the largest of the subintervals is. In this case, clearly this one is the biggest one, right? And in this case, we have 7.87. Maybe I can move this now, it gets smaller, right? I can't continue in this fashion and make it as small as I want, because at some point this one will start being the largest one, right? So if I want to make my partition small, I need more points.